He was burning brushwood in his cornfield when the ground split open in front of him. No warning. No sound from the sky. Just a crack in the earth, a thin column of smoke rising from a hole that had been there for years and had never meant anything. Until that afternoon of February 1943, when it began to breathe. Within hours, the smoke became fire. Within days, the fire became a mountain. Within 2 years, an entire town of thousands of people, a colonial church that had stood for centuries, fields that had fed families for generations, all of it was gone. Buried under lava and ash by a volcano that had not existed on any map, in any geological survey, in any human memory. 72 hours earlier, the man who watched it begin was a farmer named Dionisio Pulido. He was not a scientist. He had no instruments, no training, no framework for understanding what the ground beneath his feet was doing. He had only his eyes, and what his eyes told him was something that no human being in the modern world had ever witnessed before and has never witnessed since. The first breath of a brand new volcano. Taken from less than 30 meters away, Paricutin is the only volcano in recorded history whose entire life, from birth to death, was observed by human beings. 9 years of fire documented from the very first second, and it began in a cornfield. On an ordinary afternoon, while a man was doing the most ordinary work in the world, how does a mountain rise from flat ground in a matter of hours? What was moving beneath that field for weeks before the earth finally broke? And what does it mean that the same forces that built that volcano in 1943 are still operating right now beneath the towns and cities of central Mexico? That is what this documentary will tell you. If this story already has your attention, and something tells us it does, take a moment before we begin. Subscribe to Fury of the Earth and leave us a comment below telling us, did you know this volcano existed? We read every answer. Now let's go back to Michoacán, to a February afternoon that changed everything. The land before the fire. The Mexican state of Michoacán sits in the heart of a restless landscape. Here, the earth is not a passive stage upon which human life unfolds. It is a living, breathing, shifting presence, one that has shaped the people of this region as profoundly as any culture, any religion, or any government ever could. To understand what happened in February of 1943, one must first understand the world that existed before the fire came. Michoacán belongs to a geological zone known as the Trans-Mexican Volcanic Belt, a vast arc of volcanic activity stretching roughly 900 kilometers across central Mexico, from the Pacific coast near Colima to the Gulf of Mexico near Veracruz. This belt was not formed by accident. It is the direct consequence of the Cocos Plate, an oceanic tectonic plate, slowly and relentlessly driving itself beneath the North American plate in a process called subduction. As the Cocos Plate descends into the mantle, the immense heat and pressure cause it to release water and other volatile compounds into the overlying mantle wedge. This lowers the melting point of the surrounding rock, generating magma that rises toward the surface, seeking any weakness, any crack, any passage through which it can escape. The Trans-Mexican Volcanic Belt is the surface expression of that ceaseless underground labor. Popocatépetl, Iztaccíhuatl, Nevado de Toluca, and dozens of lesser-known peaks all belong to this family of fire. Paricutin would soon join them, though it would do so in a manner the world had never witnessed before. The village of San Juan, Parangaricuro, had existed in the Tansataro highlands for generations. Its people, the Purépecha, were among the few indigenous groups in Mesoamerica who had never been fully conquered by the Aztec Empire before the arrival of the Spanish. They were skilled craftsmen, farmers, and traders, and they carried a deep, ancestral relationship with the land beneath their feet. The soil around San Juan was rich and dark, volcanic in origin, as most of the region's soil was, and it produced crops of corn, beans, and fruit with a generosity that made life there not merely survivable, but genuinely good. The nearby town of Paricutin, little more than a small settlement surrounded by fields, shared in that agricultural rhythm. Dionisio Pulido was one of those farmers. He was a man of modest means and practical temperament, known among his neighbors as a hard-working and dependable figure. He owned and worked a small plot of land called El Llano, a cornfield not far from the village of Paricutin. There was nothing about Dionisio that history would have selected for remembrance had the earth beneath his field chosen to remain still. But the Earth had other plans. In the weeks and months before February 1943, something had been stirring in the region that most people could not have recognized for what it was. Residents of nearby communities had reported tremors, small, frequent earthquakes that rattled windows and unsettled livestock but caused no serious alarm. Seismic activity is not uncommon in Michoacán, and the local population had learned over generations to accept minor trembling as a background feature of their environment, the way a coastal people accepts the sound of waves. What they could not know was that these tremors were not random geological noise. They were the footsteps of something approaching from below. Geologists would later determine that the seismic swarm preceding Paricutin's birth lasted for approximately 2 weeks, with some accounts suggesting disturbances going back further. The tremors were shallow, originating relatively close to the surface, which is characteristic of magma forcing its way through existing rock fractures. The ground was not simply shaking. It was being broken apart meter by meter from the inside. There was another signal, one that Dionisio Pulido himself would later describe in accounts collected by researchers. In the days before the eruption, he and others noticed that a small depression or hole in his cornfield, which had been present for some time and was known locally, seemed to behave strangely. The ground nearby was warm to the touch. There were faint sounds, almost imperceptible, rising from the earth. Some witnesses spoke of a sulfurous smell drifting across the field, though not yet powerful enough to cause alarm. These were the unmistakable signs of degassing volcanic gases, primarily sulfur dioxide, carbon dioxide, and water vapor, escaping through cracks as the magma column climbed closer to the surface. None of these signs were understood for what they were. There was no volcanological monitoring station in the area. There were no seismographs calibrated to detect the specific signatures of magmatic intrusion. There was no warning system, no evacuation protocol, no scientific authority that might have interpreted the evidence and acted upon it in time. The people of the Tansitaro Highlands were entirely on their own, armed only with the knowledge of their experience and the limitations of what the naked eye and bare hand could perceive. This is not a story of negligence. It is a story of a world that simply did not yet possess the tools to read what the Earth was trying to say. On the afternoon of February 20th, 1943, Dionisio Pulido went to his cornfield to burn the brushwood from the previous harvest, as farmers do at the end of the dry season. He brought with him his wife and a neighbor. The day was ordinary. The field was ordinary. And then, from that small hole in the ground, the one that had been there for years, the one that had meant nothing, the earth exhaled. A thin column of smoke rose quietly into the cool Michoacán air. Within hours, the world would be watching. The day the earth opened, Dionisio Pulido would spend the rest of his life being asked to describe what he saw that afternoon. By all accounts, he was a patient and honest man, and he told the story the same way each time, with the careful precision of someone who understood that what he had witnessed was not something the world would easily believe. He had been working in his field. He had heard a sound like thunder, though the sky was clear, and then the ground in front of him had cracked open and begun to breathe. The initial vent was modest by the standards of what would follow. A fissure opened in the floor of a Llano cornfield, releasing smoke, fine ash, and a sharp hissing sound that witnesses described as resembling the noise of water poured onto a fire, enormously amplified. The ground trembled continuously. Small stones and clods of earth were ejected into the air. The hole widened. The smoke thickened. And Dionisio, after a long moment of standing still in the face of something his mind had no category for, turned and ran. By nightfall, the vent was throwing incandescent material into the sky. The people of the nearby villages gathered at a distance to watch, drawn by the spectacle and held back by a fear that required no explanation. The glow above the field was visible for kilometers. The sounds, described by witnesses as a continuous deep roar punctuated by sharp explosions, carried across the highland valleys and reached communities that could not yet see the flames. By the end of the first night, a cone of ejected material had already begun to form around the vent, rising with a speed that defied comprehension. What had been flat farmland at sunset was, by sunrise, a mound of ash and scoria several meters high and growing visibly by the hour. The birth of Paricutin, was not a slow geological event observed only by instruments and specialists. It was a public spectacle witnessed in real time by hundreds of ordinary people, many of whom had lived their entire lives within a few kilometers of the spot where it emerged. This is what makes Paricutin uniquely significant in the entire recorded history of volcanology. It is the only volcano in the modern scientific era whose complete life cycle, from the first crack in the earth to its final silence, was observed and documented from the very beginning. Every other volcano studied by science arrived already formed, already ancient, its origins buried in prehistory. Paricutin was born in front of witnesses and died in front of cameras. Word reached the outside world quickly. Within days, journalists and scientists were making their way toward Michoacán from Mexico City and beyond. The Mexican government dispatched geologists almost immediately, and the Smithsonian-affiliated scientific community in North America mobilized with remarkable speed for the era. Dr. Ezequiel Ordonez, one of Mexico's most respected geologists, arrived within the first week and produced some of the earliest systematic observations of the eruption. American volcanologists and geographers followed, many of them understanding instinctively that they were being offered something science had never had before. A front-row seat to the creation of a volcano. What they found when they arrived was already far beyond the modest fissure Dionisio had watched open in his cornfield. The cone that geologists would come to call Paricutin had grown at an extraordinary rate during its first days. Measurements taken in the early weeks of the eruption documented cone heights increasing by tens of meters per day during the most vigorous phases. The material being ejected was primarily basaltic andesite, a type of volcanic rock that reflects the chemical composition of the magma rising from depth magma that had formed through the partial melting of mantle rock, triggered by the subduction of the Cocos Plate far below. The eruption style in these early days was what volcanologists classify as strombolian, a term derived from the behavior of Stromboli volcano in Italy, which has been erupting almost continuously for centuries and served as an early reference point for this type of activity. Strombolian eruptions are characterized by rhythmic, moderately explosive bursts driven by large gas bubbles rising through relatively viscous magma and bursting at the surface. The result is a near-continuous shower of incandescent lava fragments, called scoria or cinders, thrown into the air and falling back around the vent to build the cone. At Paricutin, this process operated with exceptional energy, and the cone grew with a speed that astonished even experienced volcanologists. The communities closest to the eruption faced an immediate and worsening crisis. The village of Paricutin, which gave the volcano its name, was the first to be buried. Within weeks of the eruption's beginning, ash and scoria fall had made the settlement uninhabitable, and its residents were forced to abandon homes their families had occupied for generations. The displacement was not dramatic in the way of a sudden explosion or a fast-moving lava flow. It was slow, relentless, and in many ways more psychologically devastating for that quality, a burial by accumulation, 1 centimeter at a time, until the rooftops disappeared beneath the gray landscape and there was nothing left to return to. San Juan Parangaricuro, the larger and more historically significant town, watched these events from a distance of a few kilometers and prepared itself for what many residents already suspected was coming. The Church of San Juan, a substantial colonial-era structure that had stood at the center of community life for centuries, became a focal point of anxiety and, later, of one of the most visually striking images the eruption would produce. Lava flows, distinct from the cone-building ash falls, began to emerge from the base of the growing volcano within the first weeks. These flows were dense, slow-moving rivers of molten rock that advanced across the landscape with the patient, unstoppable quality of something that has never been told it cannot pass. They did not race. They crept. But they did not stop. And they were heading with the indifference that only geology can muster, directly toward San Juan Parangaricuro. The anatomy of a living volcano. To watch Paricutin was one thing. To understand it was another. As scientists arrived in the highlands of Michoacán and set up their instruments around the growing cone, they began the work of translating a raw geological spectacle into the language of measurement, classification, and theory. What they found confirmed much of what volcanology had suspected about how new volcanoes are born and revealed details that would reshaped the discipline for decades to come. Paricutin belongs to a category of volcano known as a cinder cone. The most common volcanic landform on Earth, cinder cones are relatively simple in structure compared to the Great Composite. Volcanoes like Popocatépetl or Mount St. Helens, they are built almost entirely from the loose, solidified fragments of lava called scoria or cinders that are thrown into the air during strombolian eruptions and fall back around the central vent, accumulating layer by layer into a conical shape with a bowl-shaped crater at the summit. They tend to be small by volcanic standards, rarely exceeding 300 to 400 meters in height, and they typically erupt from a single vent for a period of years before going permanently quiet. Paricutin would follow this pattern with almost textbook precision, which is part of what made it so scientifically valuable. The magma-feeding Paricutin originated deep within the mantle wedge, above the subducting Cocos Plate, as that oceanic plate descended beneath the North American plate at a rate of several centimeters per year. It carried with it water locked within hydrated minerals. At depth, under extreme pressure and temperature, that water was released into the surrounding mantle rock. Water lowers the melting point of rock dramatically, and the result was the generation of magma in a zone roughly 80 to 100 kilometers below the surface. That magma, being less dense than the solid rock surrounding it, began its slow ascent through the lithosphere, exploiting existing fractures and zones of weakness within the crust. The Trans-Mexican Volcanic Belt sits above a complex network of crustal faults and fracture zones, and it was through one of these pre-existing weaknesses that Paricutin-S magma finally found its path to the surface. The seismic swarm that preceded the eruption was the record of that final ascent, the sound of rock fracturing as the magma column forced its way upward through the last kilometers of crust. Once at the surface, the behavior of the lava was determined largely by its chemical composition and temperature. Paricutin's lavas were basaltic andesite, with a silica content intermediate between the highly fluid basalts of Hawaii and the thick, explosive rhyolites associated with calderas and supervolcanoes. This intermediate composition meant that the lava was viscous enough to trap volcanic gases, producing the rhythmic strombolian explosions that characterized much of the eruption, but fluid enough at high temperatures to flow considerable distances from the vent once it escaped as lava. Streams from the cone's base. Scientists on the ground documented two distinct but related processes operating simultaneously. The first was cone building, driven by the continuous explosive ejection of scoria and ash from the central vent. The second was lava effusion, in which magma emerged more quietly from vents and fissures at the base of the cone and spread outward across the landscape as slow-moving lava flows. Both processes fed on the same magma source, but they expressed it in dramatically different ways and posed very different threats to the surrounding communities. The lava flows from Paricutin were not fast. By volcanological standards, they were almost leisurely, advancing at rates that a person could comfortably outpace on foot. But their temperature, exceeding 1,000 degrees Celsius at the point of emission, and their sheer volume made them unstoppable by any means available at the time. As the flows advanced, they cooled and solidified at their edges and upper surfaces, forming a crust of dark, rough rock known as a lava, while the molten interior continued to move beneath, occasionally breaking through the hardened shell and sending new lobes of liquid rock creeping forward into the fields and forests ahead. The scientists observing all of this were acutely aware that they were witnessing something without modern precedent. Volcanology in the 1940s was still a relatively young science, and the tools available, basic seismographs, temperature probes, chemical sampling equipment, and careful visual observation were modest by contemporary standards. Yet the researchers who worked at Paricutin during its active years produced an extraordinary body of documentation. They mapped the growth of the cone at regular intervals, measured the volume and advance rate of lava flows, collected gas and rock samples, and compiled records of seismic activity that would serve as reference material for generations of volcanologists who came after them. Paricutin was not just a volcano. It was a natural laboratory that arrived fully equipped and asked only that Science pay attention. The slow erasure of San Juan Parangaricuteraether is a particular kind of loss that does not announce itself with a single catastrophic moment. It arrives gradually, incrementally, with a patience that seems almost calculated to exhaust the human capacity for resistance. The destruction of San Juan Parangaricuro was that kind of loss. It did not happen in an afternoon. It happened over months and then years, and the people who lived through it were forced to watch with a helplessness that no sudden disaster could have imposed so completely. San Juan Parangaricuro was not a small or insignificant place. Founded in the colonial period, it was a town of several thousand inhabitants with a functioning economy built around agriculture, craftsmanship, and trade. At its center stood the parish church of San Juan, a substantial stone structure that had served as the spiritual and architectural heart of the community for generations. The church was not merely a building. It was the physical expression of a community's identity, the place where its people had been baptized, married, and mourned for centuries. When the lava came for San Juan, it came for all of that. The lava flows that emerged from the base of Paricutin's cone began advancing toward San Juan Parangaricuro in the early months of the eruption. Their movement was slow enough that residents could observe their progress daily, measuring the advance in meters rather than kilometers, watching the black frontier of solidified rock edge closer across fields that had recently been green. This slowness was in some ways a mercy. It allowed for evacuation, for the removal of possessions, for the painful process of decision-making that sudden disaster does not permit. But it was also a form of prolonged torment, because it gave the community time to understand fully what was being taken from them, and no time at all to prevent it. The Mexican government organized the relocation of the population of both the village of Paricutin and the town of San Juan Parangaricuro to a new settlement established approximately 27 kilometers away, which was named New San Juan Parangaricuro. The logistics of this relocation were complex and emotionally devastating. Families dismantled what they could carry, loaded ox carts and trucks with furniture, tools, religious objects, and personal belongings, and made the journey to a place that was geographically safer but spiritually empty, a town that had a name but not yet a history, streets but not yet memories. The Purépecha people, who formed the majority of the population, carried with them something that could not be loaded onto any cart, a relationship with a landscape that was now being consumed. The fields where their families had farmed for generations were disappearing beneath meters of lava and ash. The paths between settlements, the hills visible from kitchen windows, the specific quality of light on a particular valley at a particular hour, all of it was being erased. Slowly and completely by a process that recognized no human claim upon the land. By 1944, lava flows had reached the outskirts of San Juan Parangaricuro. The advance was uneven, following the natural contours of the terrain, filling low areas first and sparing higher ground temporarily before surrounding and isolating it. Buildings on the edges of town were engulfed first, their walls cracking under the thermal stress of the approaching rock, then disappearing beneath the advancing flow as the lava pushed through doorways and windows and finally over rooftops. The process was silent in the way that immense slow things are silent. There were no explosions, no dramatic collapses. Just the steady, quiet advance of black rock over everything that had been built and planted and loved. The Church of San Juan was among the last structures to be reached. Its stone walls and elevated position gave it a temporary resistance that the surrounding buildings did not possess. But the lava was not deterred by architecture or by the weight of what a building represented. It rose around the church's base, filled the surrounding streets, climbed the exterior walls, and eventually buried everything except the upper portions of the facade and the twin bell towers, which remained standing above the hardened lava field like the masts of a ship that has settled to the bottom of a dark sea. This image, the towers of San Juan rising from a frozen ocean of black volcanic rock, would become one of the most enduring and widely reproduced photographs associated with the Paricutin eruption. It appeared in newspapers and scientific journals across North America and Europe, and it communicated something that pages of geological description could not: the scale of what had been lost, and the strange, terrible beauty that loss can sometimes produce. The scientific community observing the eruption documented the lava's advance with careful measurements and photography, producing records that remain valuable to researchers today. But the scientists also noted something in their field journals that went beyond pure data, an awareness that they were witnessing not only a geological event but a human catastrophe unfolding in slow motion, and that the two could not be cleanly separated. The Earth that was being studied was also the Earth that was being taken from people who had no say in the matter and no recourse against it. That tension between the scientific value of observation and the human cost of what was being observed would remain present throughout the years of Paricutin's activity, a quiet discomfort beneath the intellectual excitement of discovery. 9 years of fire volcanoes do not operate on human schedules. They do not respect harvests or holidays or the exhaustion of the people living in their shadow. Paricutin erupted continuously for 9 years, from February 1943 to March 1952. And across that span it passed through phases of furious intensity and relative quiet, of ash storms that darkened the sky for hundreds of kilometers and periods of reduced activity that allowed scientists to approach the cone and collect samples from its still steaming flanks. The eruption was not a single event. It was a prolonged geological conversation between the deep earth and the surface, conducted in the language of fire and stone. The first year was the most violent. During 1943, Paricutin ejected the majority of its total lifetime volume of material, building its cone with extraordinary speed and establishing the lava fields that would ultimately cover approximately 25 square kilometers of the Tansitaro highlands. The cone reached a height of roughly 336 meters above the original surface level of El Llano cornfield within its first year, a rate of vertical growth that has rarely been documented in any volcanic system anywhere in the world. Scientists measuring the cone's dimensions at regular intervals produced growth curves that looked less like geological records and more like the ascent graphs of a rapidly inflating structure. The eruptive activity during this early phase was dominated by what volcanologists describe as violent strombolian behavior, occasionally intensifying into subplinian episodes in which eruption columns rose several kilometers into the atmosphere, carrying fine ash particles that were distributed across enormous distances by upper-level winds. Ash fall from Paricutin was recorded as far away as Mexico City, more than 320 kilometers to the east, where residents reported gray powder settling on streets and rooftops during the eruption's most energetic periods. In the immediate vicinity of the volcano, ash accumulation was measured in meters rather than centimeters, burying vegetation, collapsing roofs, contaminating water sources, and rendering large areas of previously productive farmland permanently unusable. The relationship between ashfall and agriculture was one of the most consequential and least dramatic aspects of the eruption's impact. Unlike lava flows, which advanced visibly and could be photographed and measured with relative ease, ashfall worked invisibly and cumulatively. Fields that received moderate ash deposition might recover after several seasons, as volcanic material is often rich in minerals and can eventually enhance soil fertility. But fields buried under heavy accumulations of sterile scoria and fine ash faced a recovery timeline measured in decades or generations, if recovery came at all. The agricultural economy of the Tansitaro region, already disrupted by the displacement of its population, was effectively destroyed across a wide area surrounding the volcano. As the first year gave way to the second and third, the eruption's character began to shift. The explosive strombolian activity remained, but its intensity fluctuated in patterns that scientists worked to correlate with changes in the underlying magma supply and the opening and closing of conduits within the volcanic system. Periods of reduced explosive activity were often accompanied by increased lava effusion, as if the magma, finding the explosive pathway temporarily restricted, sought alternative routes to the surface through lower pressure fissures at the cone's base. This alternation between explosive and effusive behavior is a characteristic feature of many cinder cone eruptions and reflects the dynamic balance between magma pressure, gas content, and conduit geometry operating at depth. The scientific teams working at Paricutin during these middle years established monitoring protocols that were innovative for their time. Researchers from Mexican institutions, the United States Geological Survey, and several American universities maintained a near-continuous presence in the field, rotating personnel and sharing data in a collaborative arrangement that prefigured the international volcanic monitoring networks that would develop more formally in later decades. They measured ground deformation using careful surveying techniques, tracked changes in the volcano's thermal output, and conducted systematic sampling of lava and gas emissions to monitor changes in the magma's chemical composition. Over time, one of the more significant scientific findings to emerge from this sustained observation was the documentation of a gradual change in the composition of Paricutin's erupted materials. Over the course of the eruption, the earliest lavas were relatively rich in magnesium and poorer in silica, suggesting a source magma that had experienced less contamination from the surrounding crustal rocks during its ascent. As the eruption continued, the chemical signature of the lavas shifted subtly, indicating that the magma supply was evolving, possibly drawing from slightly different source regions within the mantle, or experiencing greater interaction with crustal material along its pathway to the surface. These compositional changes, modest in absolute terms, told a story about the deep plumbing system feeding the volcano that no surface observation alone could have revealed. Through all of this, the landscape around Paricutin was being remade with a thoroughness that geological processes rarely achieve on human timescales. Forests were buried or killed by ashfall. Rivers and streams were dammed or redirected by lava flows, creating new drainage patterns across the highland terrain. The topography of an area spanning many square kilometers was fundamentally altered, producing a landscape that bore no resemblance to what had existed before February 1943 and that would persist, largely unchanged, for centuries to come. The 9 years of Paricutin's activity compressed into a single, human lifetime what geological processes typically require thousands of years to accomplish. For the scientists who observed it, that compression was an extraordinary scientific gift. For the people who had lived on that land, it was simply loss accumulated year by year, without relief or remedy. The scientists who lived with the fire science is often imagined as a clean and orderly enterprise, conducted in controlled environments by people working at a comfortable distance from their subject. Paricutin dissolved that illusion entirely. The researchers who came to study this volcano did not observe it from behind glass or from the safety of remote sensing stations. They walked its flanks while it erupted. They breathed its gases, dodged its falling cinders, and camped within sight of its glow on nights when the ground trembled beneath their sleeping bags. The science produced at Paricutin was inseparable from the physical experience of being present in an active volcanic landscape, and the people who produced it understood that they were working at the boundary between knowledge and genuine danger. The figure who did the most to establish systematic scientific observation at Paricutin in its early years was Dr. William F. Fauchag of the Smithsonian Institution, who arrived in Mexico shortly after the eruption began and spent considerable time in the field over the following years in collaboration with Mexican geologist Genaro González Reyna. Together, they produced a foundational monograph on the eruption that documented its physical characteristics, geological context, and impact on the surrounding landscape with a thoroughness that reflected both scientific rigor and genuine personal engagement with the subject. Fauchag's observations during the earliest and most violent phase of the eruption provided the scientific community with its first detailed account of a cinder cone's birth and rapid growth, a contribution that remained a primary reference in volcanological literature for decades. Other researchers came from universities across the United States and Mexico, drawn by the recognition that Paricutin represented an opportunity that the geological sciences might never see again. Geomorphologists studied the way the lava flows modified the existing terrain. Petrologists analyzed the chemical and mineralogical composition of the erupted materials, in search of information about the magma source. Geophysicists deployed seismographs to monitor the continuing tremors that accompanied the eruption and worked to distinguish between signals generated by magma movement and those produced by the mechanical settling of the growing cone. Atmospheric scientists tracked the distribution of ash and volcanic gases across the region, producing some of the earliest systematic data on how volcanic emissions interact with local and regional weather patterns, the logistical challenges of conducting science in an active volcanic environment in rural Michoacán during the 1940s were considerable. The roads leading to the area were poor, and the additional traffic generated by the eruption's notoriety, journalists, tourists, government officials, and scientists all converging on the same narrow highland routes, made access unreliable. Equipment had to be transported by mule over the last stretches of terrain where vehicles could not pass. Communications with the outside world were slow, dependent on postal service and occasional telephone connections that the eruption itself sometimes disrupted by damaging infrastructure. Researchers working extended field seasons in the area lived in conditions that were Spartan by any measure, housed in local structures or temporary camps that offered little protection against the ash falls that periodically blanketed the region. Despite these difficulties, the quality and consistency of the observations produced at Paricutin were remarkable. Part of the reason was the nature of the volcano itself. Cinder cone eruptions, while energetic, are generally predictable enough in their behavior to allow researchers to approach safely during periods of reduced activity and retreat to distance when explosive episodes intensified. Paricutin was dangerous, but it was not capricious in the way that more silicic volcanoes can be, where sudden explosive transitions offer no warning and no margin for error. Scientists learned the volcano's rhythms and worked within them, developing an intuitive understanding of its behavior that complemented the data. Their instruments were collecting local knowledge proved invaluable in this process. The Purépecha residents who remained in the area as guides, laborers, and informants possessed a detailed familiarity with the terrain that no visiting scientist could replicate quickly. They knew the paths through the lava fields, the locations where gases accumulated in dangerous concentrations in low-lying areas, and the subtle signs in the volcano's behavior that suggested heightened risk. This collaboration between formal scientific expertise and indigenous environmental knowledge was not always acknowledged explicitly in the published literature of the era, reflecting the limitations of mid-20th century scientific culture. But it was nonetheless essential to the work that was accomplished. The documentation produced at Paricutin during its 9 active years also extended beyond the purely scientific. Photographers and filmmakers, some working independently and others in collaboration with research teams, produced an extensive visual record of the eruption that captured dimensions of the event that written description and numerical data could not convey. The images of lava-consuming buildings at the edge of San Juan Paringaricuro, of the cone silhouetted against a sky lit orange by its own emissions, of ash-covered fields stretching to the horizon. These photographs circulated widely in the international press and introduced the general public to the reality of volcanic geology with an immediacy that no textbook illustration could match. Paricutin made volcanology visible to the world in a way it had never been before. And in doing so, it changed not only what scientists knew about how volcanoes work, but what ordinary people understood about the living, restless nature of the ground beneath their feet. The final years and the last breath by the late 1940s. Paricutin had settled into a rhythm that was still geologically extraordinary but had become, for those living and working in its vicinity, something approaching familiar. The cone stood as a permanent feature of the highland skyline, its summit trailing a near-continuous plume of gas and ash that local residents had long since incorporated into their understanding of the landscape. The most violent phase of the eruption was behind it. The lava flows that had consumed San Juan Paringaricuro had largely solidified into the dark, fractured terrain that now occupied what had once been farmland and forest. The immediate humanitarian crisis had been absorbed, imperfectly and painfully, into the slower processes of relocation and adaptation. And the scientific community, while maintaining its observation programs, had begun the work of synthesis, of organizing 9 years of accumulated data into a coherent account of what Paricutin had revealed about the mechanics of volcanic birth and growth. The volcano, however, had not finished speaking. In 1947 and again in the early 1950s. Paricutin produced episodes of renewed activity that reminded observers that a volcano operating within its active lifetime remains capable of significant behavioral change. These later phases were characterized by shifts in the location of active venting on the cone,
the opening of new fissures on its flanks,
and periods of intensified lava effusion that sent fresh flows across terrain that had already been modified by earlier activity. The cone itself underwent morphological changes as portions of its structure collapsed or were modified by the internal pressure of continuing magma supply, producing asymmetries in its profile that geologists documented carefully as evidence of the dynamic processes operating within the edifice. The chemical composition of the erupted materials continued its gradual evolution. During these final years, researchers analyzing lava samples from the later phases of the eruption noted increased silica content relative to the earliest flows, a change consistent with the interpretation that the magma source was evolving over time, either drawing from a region of the mantle that had experienced greater crustal contamination, or reflecting the progressive differentiation of the magma body itself as it cooled and crystallized within its subsurface reservoir. These compositional trends, documented through painstaking laboratory analysis of field-collected samples, provided some of the most detailed geochemical data on the temporal evolution of a single eruptive episode that volcanology had yet produced. Through 1951 and into early 1952, the signs of waning became increasingly apparent to experienced observers. The height and vigor of the eruptive column diminished. The frequency and intensity of strombolian explosions decreased. The volume of lava being effused from the cone's base dropped measurably. Seismic activity, which had accompanied the eruption continuously since before its surface manifestation, in February 1943 began to quiet. These changes were consistent with a reduction in the rate of magma supply from depth. The deep source that had fed Paricutin for 9 years was, for reasons that could be inferred but not directly observed, delivering less material to the surface. The end, when it came, was anticlimactic in the way that endings often are when they have been approached gradually over a long period. On February 25, 1952, eruptive activity at Paricutin effectively ceased. There was no final explosion, no dramatic conclusive event that marked a clear boundary between active and extinct. The volcano simply became quieter and quieter, the emissions from its summit diminishing from a robust plume to a thin wisp of gas and then to nothing. Scientists monitoring the site noted the cessation and continued their observations for weeks and months afterward, alert to the possibility of renewed activity. Before concluding that the eruption had genuinely ended, the cone stood 424 meters above the level of the original cornfield, a figure that placed it near the upper range of height for cinder cone volcanoes globally. The lava fields surrounding it covered approximately 25 square kilometers. The total volume of material erupted over 9 years was estimated at roughly 1.3 cubic kilometers, a modest figure by the standards of major volcanic eruptions, but an extraordinary output for a single cinder cone operating over a defined and documented lifespan. What the numbers could not capture was the qualitative transformation of the landscape. The Tansitaro Highlands in Yizhou bore no resemblance to what they had been in 1943. The terrain that had supported a functioning agricultural society, with its towns and fields and roads and forests, had been replaced by a volcanic landscape of stark, almost lunar character, black lava fields broken by the occasional surviving wall or church tower. Dissected by the gullies that formed as rainfall began the slow work of eroding the ash deposits, punctuated by the stark cone itself rising above everything it had buried. Dionisio Pulido, the farmer in whose field the volcano had been born, lived to see its end. He died in 1958, 6 years after the eruption ceased, having spent his final years as a figure of considerable local and international curiosity, the man who had watched a mountain emerge from his cornfield and had lived to tell the story. He told it by all accounts without embellishment and without bitterness. What had happened had happened. The earth had done what the earth does, and he had been standing in the right place or the wrong place, depending entirely on how one chose to measure such things. What the volcano left behind when a volcano goes silent, the world it has made does not immediately reveal its full meaning. The landscape of Paricutin in Yizhou was raw and unfinished in the way that all new geological surfaces are, a terrain without soil, Without vegetation, without the accumulated biological and cultural history that gives a landscape its depth and legibility. The lava fields were black and fractured, their surfaces broken into the sharp, irregular forms characteristic of solidified lava, hostile to walking and inhospitable to the seeds that wind and birds occasionally carried across them. The ash deposits on the surrounding slopes were unstable, subject to erosion by rain, that now moved across a surface stripped of the roots and organic matter that had previously held it in place. The two buried towns existed somewhere beneath this new landscape, preserved in a form that was neither ruin nor memory, but something between the two. Yet even in its immediate aftermath, the transformation that Paricutin had imposed on the Tansataro highlands carried within it the seeds of recovery. Volcanic landscapes, for all their initial sterility, are among the most fertile environments on Earth once the processes of ecological succession begin their work. The minerals locked within basaltic rock are released slowly by weathering into forms that plants can use. And the porosity of volcanic deposits creates soil structures that retain moisture with unusual efficiency once organic matter begins to accumulate. The question was not whether life would return to the slopes of Paricutin, but how long the process would take and what form it would assume. The answer came gradually, over years and then decades. Pioneer plant species, adapted to colonizing bare mineral surfaces, were among the first to establish themselves in the ash fields at the margins of the lava flows. Mosses and lichens appeared on the surfaces of rocks within a few years of the eruption's end, their slow metabolism beginning the millimeter by millimeter work of breaking down the volcanic surface and creating the thin organic layer that more complex plants require. Grasses followed, then shrubs, then the first young trees at the edges of the lava field where soil had accumulated in sheltered pockets. The process was not linear or uniform. It proceeded faster on north-facing slopes where moisture was retained longer, slower on exposed ridges where erosion competed with accumulation, and hardly at all on the densest portions of the lava field where the surface remained essentially impenetrable to roots for many years for the displaced. Communities of San Juan Parangaricuro and the village of Paricutin. The ecological recovery of the landscape was a process observed from a distance, from the settlement of New San Juan Parangaricuro, where the relocated population had been rebuilding their lives since the early years of the eruption. The relationship between the displaced communities and the landscape that had been taken from them was complex and did not resolve simply with the eruption's end. People returned periodically to the site of the old town, navigating the lava fields to reach the still-standing towers of the Church of San Juan, which had become both a pilgrimage destination and a site of continued communal mourning. The towers remained a focal point of identity for a community whose physical home had been destroyed but whose attachment to that specific place had not diminished with distance or time. The scientific community's engagement with Paricutin also continued long after the eruption ended. The site became a natural laboratory for the study of volcanic landscape evolution, offering researchers the unusual advantage of knowing with precision when the surface they were studying had been created. This temporal certainty, rare in geological research, allowed scientists to construct detailed chronologies of erosion, soil development, and ecological succession that would have been impossible to establish on older volcanic surfaces whose history was obscure. Studies conducted at Paricutin in the decades following the eruption contributed significantly to the understanding of how volcanic landscapes recover and evolve, providing data that informed research at other volcanic sites. Around the world, the cone itself became a destination for volcanologists seeking to study the internal structure of a cinder cone whose formation history was completely documented. The erosion that began immediately after the eruption's end slowly exposed cross-sections of the cone's interior, revealing the layered structure of alternating scoria deposits and lava intrusions that recorded the successive phases of the eruption in physical form. These exposures allowed researchers to read the cone's history directly from its stratigraphy, connecting the visible layers to the observational records compiled during the eruption years and producing a level of interpretive precision that older, more deeply eroded cinder cones could not provide. Paricutin also entered the broader cultural landscape in ways that extended well beyond the scientific community. It was designated one of the 7 natural wonders of the world by some popular classifications, a recognition that reflected its unique status as the only volcano whose complete life cycle had been witnessed by modern observers. Tourism to the site developed steadily in the decades after the eruption, with visitors making the journey by horse or on foot across the lava fields to reach the church towers of San Juan and, for those willing to undertake the longer trek, the summit of the cone itself. The landscape that had represented catastrophe and loss for the people who had lived there became, for visitors arriving from outside, a place of austere and powerful beauty, a reminder that the earth operates according to its own aesthetic, indifferent to human preferences but capable, in its indifference, of producing something that human sensibility cannot help but find magnificent. The lesson that never ends: a volcano that has gone silent is not a volcano that has ceased to matter. Paricutin in the decades following its 1952 cessation became, if anything, more significant to science and to human understanding than it had been during the dramatic years of its activity. The eruption itself was the event. What came after was the meaning, the slow, patient work of extracting from 9 years of geological spectacle the deeper lessons about how the Earth functions, how human communities absorb catastrophic change, and what it means to live on a planet that remains, beneath every surface we have built upon it, fundamentally and permanently alive. The monitoring of Paricutin did not end with the eruption. Mexican geological authorities and international research teams maintained observation programs at the site for years after the last emissions faded from the cone's summit, alert to any signs of renewed activity and committed to documenting the post-eruptive evolution of the landscape with the same systematic care that had characterized the observation of the eruption itself. Ground deformation surveys, conducted using increasingly precise instrumentation as technology advanced through the latter half of the 20th century, tracked the subtle subsidence of the terrain as the subsurface magma body that had fed the eruption slowly cooled and contracted. Gas monitoring at fumarolic vents on the cone's flanks continued intermittently, providing data on the gradual decline of residual hydrothermal activity. Seismic networks in the broader Trans-Mexican Volcanic Belt region captured the background tremor of a tectonically active zone that had produced Paricutin and retained the capacity to produce future events of similar or greater magnitude. That capacity for future events is perhaps the most important practical legacy of Paricutin for the communities and governments of central Mexico. The Trans-Mexican Volcanic Belt is not a geological feature of the past. It is an active system, driven by the continuing subduction of the Cocos Plate beneath the North American plate, a process that operates on timescales of millions of years and shows no signs of cessation on any timescale relevant to human civilization. The same conditions that produced Paricutin in 1943 exist across a broad zone of central Mexico, where the crust is thin, faulted, and underlain by a mantle wedge capable of generating magma given the right triggering conditions. Volcanologists studying the region have identified numerous areas where future monogenetic eruptions, single-event volcanic outbursts like Paricutin, emerging from new vents rather than from established volcanic edifices, are considered geologically plausible within timeframes that human societies must take seriously. The challenge this presents to modern volcanology and emergency management is considerable. Monogenetic eruptions are among the most difficult volcanic events to predict precisely because they do not occur at fixed, known locations, unlike composite volcanoes such as Popocatépetl, which can be monitored continuously at a defined site with established instrumentation. A future Paricutin could emerge anywhere within a broad zone of volcanic potential, with warning times measured in days or weeks rather than months or years. The seismic precursors that preceded the 1943 eruption, the swarm of shallow earthquakes that lasted approximately 2 weeks before the surface vent opened, would today be detectable by modern seismic networks with far greater sensitivity and spatial resolution than anything available in the 1940s. But detection is not the same as prediction, and the gap between knowing that something is happening beneath The ground and knowing precisely where and when it will reach the surface remains a fundamental limitation of the science. The communities living within the Trans-Mexican Volcanic Belt have absorbed these realities into their relationship with the landscape in ways that vary considerably across the region. Some communities maintain strong institutional connections to volcanic hazard assessment programs operated by Mexican governmental agencies and university research centers. Others rely more heavily on traditional environmental knowledge and the kind of attentive, experiential familiarity with local geological behavior that Dionisio Pulido's neighbors possessed in 1943 knowledge. That was real and valuable, but ultimately insufficient to provide adequate warning of what was coming. The integration of scientific monitoring with community-level hazard awareness remains an ongoing challenge, one that Paricutin illuminated with particular clarity, and that has not been fully resolved in the 8 decades since the eruption began. Beyond the practical dimensions of hazard assessment and emergency preparedness, Paricutin carries a philosophical weight that distinguishes it from most geological events. It is one of the very few moments in human history when the creation of a significant landform was witnessed from its first instant by people who could describe what they saw, record what they measured, and reflect on what it meant. Every mountain, every valley, every volcanic cone that existed before the modern era carries its origins in silence, processes that occurred without witnesses, without documentation, without the human presence that transforms an event into a story. Paricutin alone among the world's volcanoes was born into history rather than into geology, arriving in a world equipped to observe it and curious enough to do so without interruption for the entirety of its active life. What Dionisio Pulido saw rising from his cornfield on the afternoon of February 20th, 1943, was not simply a geological phenomenon. It was a reminder, delivered with the force and finality that only the Earth itself can muster, that the surface we inhabit is not a fixed and permanent stage but a temporary arrangement of materials that the planet has not finished reorganizing. The ground beneath every field, every city, every road ever built is subject to the same forces that open that fissure in Michoacán, forces that operate without reference to human plans, human histories, or human attachments to the places we have made our own. That is not a cause for despair. It is an invitation to humility and to the kind of attention that Paricutin demanded and rewarded in equal measure. The Earth is speaking always. The question is whether we have learned, in the 8 decades since a farmer watched a mountain rise from his field, to listen with sufficient care.